Okay, good. So let's go to the second talk of this session. The speaker is Neil Olver, that is one of the local organizers of the World Conference, and he's going to talk about improved approximation algorithms for inventory problems. And yeah, the floor is yours.
Thanks very much, Laura. I think there's someone who's not muted.
I'm muting right now, so I think you have to unmute yourself now, Neil.
Okay, sorry, I had to find it. Okay, perfect, thank you. So this is a joint work with Thomas Bosman, who was a student in Amsterdam and is now working for Booking.com. And so this is about a problem, it's called the inventory routing problem. So let me explain this problem. So, hang on. Of course, nothing is working. Okay. Yeah, so for some reason, okay, very good. So what is the inventory routing problem? So we're given a metric space with one distinguished node, the root R, and think of this root as being some kind of factory. It's producing one type of good. And then all the other points in the metric space are, say, warehouses or shops where we need to deliver goods to. And we have demands for our product at each of these locations. And actually, we have demands per time unit. Let's say that each time period is a day. Then we have a sequence of demands at each location. So on day 1 at this location, the demand is 2. On day 2, the demand is 5 for some period of time, capital T. So there are T time periods. And we have this information for all locations. So this is not an online problem. So we have this information for every location, for every time period, we have a demand. And we have to satisfy this demand from our factory by sending out a vehicle delivering the goods. And in the version of this problem I'm going to talk about, there's no capacity constraints, so we can put as much product in our vehicle as we like. And so one thing we could do is on day 1, we send out our truck, and let's say I send it out to the 3 locations here, which actually had demand on day 1. And then on day 2, I could send out my truck to every location which has a demand of day 2 and so on. That's one thing I could do in this problem. And then we would essentially just have a traveling salesman problem to solve on each day. Okay, so that would just essentially just be TSP. So what's going to make this problem different is that we are allowed to deliver product early. Okay, so we can deliver a product that's going to be used in day 2 on day 1, but we have to pay for it. Okay, so this in sort of applied settings, you know, this is motivated by some kind of sort of delivery system where the supplier is managing the inventory instead of the customer. So we can deliver early, but we have to pay for the warehouse space. Let's say it's a cost of 10 per item per day. And it could depend on the location. It could be more complicated, but let's just say it's 10 per item per day. So now maybe what's better is on day 1, we might deliver to all the locations, and we'll deliver some extra goods here and here. And but maybe I won't. I mean, I could also deliver 5 extra units over here, but maybe I'm not going to do that because the holding cost might be a bit expensive. So instead, on day 2, I will just go to this location to deliver the 5 goods, but I don't need to go anywhere else. Okay, that's the inventory routing problem. So just to summarize, we're given our metric space, given the route, we're given demands, how much of the good we want at each location at each time. And we have these holding costs, which in general could be somewhat arbitrary. So it could depend on the location, could depend on the time period, but you should just think about linear holding costs. So for each location, the holding cost is proportional, per day. Okay, a solution, I'm going to specify the solution as a set ST that we deliver to on day T. Okay, once we've decided on this, everything else is sort of relatively easy, modulo solving a TSP problem. So firstly, once I know the set I'm going to deliver to on day T, well, there's a TSP problem on that set that I should solve. I'm not going to be worried about constant factors here. So for us, that's, we solve that with a constant factor approximation. That's going to be fine. And so we know how much we're going to pay for delivery on day T. And we also know exactly how much to deliver to each location, because it's clear, right? I should look at the next time that I visit that location after the current point of time, and everything in between I need to deliver on day T, right? So if I don't visit a location V from day 10 to day 20, well, then I must satisfy all the demand up to day 19 when I deliver on day 10. Okay, so this is our objective at the bottom. So this is capturing the TSP cost. And then this is capturing the holding cost. Don't worry too much about pausing it. It's just, that's the holding cost. So that's the model. If there are any questions about the problem, happy to take them now rather than waiting. So if there are any questions, let me know now.
I don't see any hand raised. Perfect. Yeah, one.
Yes.
Is it important to assume linear holding costs by Joe Butt?
Yeah, so well, there are some existing results which use some structure on the holding costs. I'll come to that, but results that I will talk about will not depend in any way on the holding costs. Will work for anything. Thanks.
Perfect.
Any other questions?
Any other question about the model? No. Okay, you can go ahead.
Okay. And let me just mention, so I'm not going to be worried about constant factors. And so the fact that this is a TSP problem, I can just as well think of this as being a spanning tree problem or a Steiner tree problem, anything like that. Anything that's within a constant factor of the TSP tour for me will be exactly the same. Okay. We're not going to be worried about that. Okay. So this problem, another reason I wrote it in this form is that this is there's a related problem that looks very similar, which is if I just keep the same problem except I change this cost function f IRP, which represented TSP cost or minimum spanning tree cost, to some other function. So the problem is called subadditive GRP, so joint replenishment problem, if f is just some arbitrary subadditive function, and if it's monotone, if it's submodular and monotone, we will call this the submodular joint replenishment problem. And that's also been studied. I'll come to more of the literature in a moment, but this version was studied by Chung et al. And let me just make clear right now that these are sort of incomparable problems, and that the inventory routing problem, the TSP cost function or the MST cost function is not submodular, not even in some approximate sense. So both are sort of natural. So f being an arbitrary monotone submodular function is a very natural problem. F being the specific TSP cost is a natural problem. They're incomparable. So what is known about these problems? So on the left is for the inventory routing problem, for the right is for the submodular joint replenishment problem. So one thing let's start on the left. So one thing that's easy is log n, where n is the number of nodes in the metric space. So that's just tree embedding. Plus, okay, one has to be able to solve this on trees. It's not trivial, but that can be done. So that's log n. And then there was also a paper by Fukunaga, Nikzad, and Ravi, where they looked at a variant of this problem where where it's periodic in the sense that the tours or the set of nodes that visit on each day, if you look at a particular location, you visit that on a periodic schedule, once a week, once a day, something like that. Okay, so that was looked at, and that has a constant factor. Was there a question or no?
I don't see any.
Okay, thanks. On the right is for submodular JRP, so that also has a sort of a logarithmic log n plus log t by Chung et al. Obviously, this is not based on tree embedding because there's no longer any metric structure here. F could be any submodular function. And then they also gave constant factors for many special cases of F. Okay. And then there was a paper by Najera, Zhan, and Shi where they gave a log t approximation for both. I will come back to this paper in a bit. And in fact, a little bit better for linear holding costs, actually more general than that, but under some restrictions on the holding cost, including linear, they beat the sort of logarithmic bound, so log t over log t. And of course, I mean, a natural open question is, can we get constant factors for either of these problems? So we won't resolve that here, but what we do is we give an exponential improvement for both. So we get log, and in fact, the minimum of number of points in the metric space, and t for IRP, and the same thing for submodular joint replenishment. Okay, so now n is not points in the metric space, but it's the ground set of the submodular function. Okay, so not quite constant, but much better. And I think it's, I mean, I guess this makes me very strongly believe there should be a constant factor for both. So, okay, so let me say a little bit about the techniques that we use. So the first thing we're going to do is exploit something that in this paper by Najera, Zhan, and Shi, which is we can relate this to a different problem. And this different problem has no holding costs at all. And as follows. So we still, I'm going to just talk about IRP here. So we still have our metric space, our locations. And now what we have is for each location, we have an interval of time. So these vertical lines represent days, so time periods. Each demand has an interval, and we must satisfy the demand within that interval. So here, V1 has the interval 1, 2, 3. It means we must visit V1 somewhere, at least one of those 3 days. Okay. V2 must be visited on one of the days 3, 4, 5, 6, and so on. Okay. But there are no holding costs as long as we deliver somewhere on those set of days. So in this example, I could deliver on days 3 and 7 only by visiting 1, 2, 3 on day 3 and 4, 5 on day 7, and that's a feasible solution. The cost is the sum of those two tour costs. Okay, so no holding costs, and it turns out that yeah, well, okay, so let me just actually say this, of course, has a simple natural IRP formulation, which in turn has it's a covering formulation where I just have a variable for each day and each possible subset. Okay, so YST represents that I visit precisely the set S on day t. Okay. And if we relax that, we will get a natural LP formulation. This has an exponential number of variables, not a problem. The usual tricks allow us to solve this. Okay, so what is the relationship? Well, basically, if we can solve this interval problem, we can solve the IRP problems. This is by measure Zhan and Xi. As long as it's an LP relative approximation algorithm for this for this interval problem, then we're good. Okay, I won't say too much about it, except that it's a filtering argument. So basically, if you look at a similar natural LP for the inventory routing problem, then a particular sort of demand could be satisfied in a fractional way. And then you sort of look at the median of this and say, okay, well, half of this demand is satisfied to the left, which is going to be kind of expensive, and half of it is satisfied within this interval, and I'll use this as my interval and double everything. Anyway, it's a fairly standard filtering argument once you know what you're looking for. Okay, so we only have to think about this interval problem. And one thing one might consider thinking about is that, well, now we have these intervals. If there's some nice structure on these intervals, maybe things are easier. And in particular, it's nice to think about a laminar structure on these intervals. So that might seem nice. And in fact, well, we can't quite simplify the problem to laminar intervals, but we show that it's sufficient to solve the following type of instance. Basically, start with a laminar family, and in fact, a laminar family like I've shown, where things are sort of dyadic, so the time periods are just doubling kind of at each level up the laminar family. So start with a laminar family like that, and now you're allowed to shrink each interval, but only from the right. Okay, so the left endpoints of these intervals are staying the same, but I can remove anything from the right of the interval. That's what we call a left-aligned family. And we show that it's sufficient to solve the problem for left-aligned families. So basically, we show you can take any instance, decompose it into a left-aligned instance and a similar right-aligned instance, which is exactly the mirror image. And if you solve both of these instances, you can combine it to get a full solution. So it's not quite as nice as laminar, but it turns out that we get a lot of the advantages of a laminar family from this structure. For most of the rest of the talk, probably all the rest of the talk, I'll only talk about laminar families. Okay, one other small but important simplification is that we can actually show that T can be bounded polynomially in N. So given that it's sufficient to show, so if we want to get a log-log minimum of N and T approximation, well, we just need to show something that's logarithmic in the number of levels of this laminar family, because the number of levels in this dyadic laminar family will be bounded by log of T. So that's our goal, okay? An approximation, which is order log number of levels. Okay, so let me this will be somewhat hand-wavy, but I'll just give you an idea of how this works in the last 5 minutes. So it's going to be a randomized iterated rounding procedure. So we're going to start with a fractional solution to this LP that I've already described. So YST is kind of saying fractionally that on day t, we're visiting this set S, right? So if YTS was 1, it means we visit exactly the set S on day t. Now we have a fractional solution where every location is covered, meaning if I sum up, so if I look at any location and sum up over its time interval, this FE is meant to be the time interval, and sum up over all of the sets that contain it, the coverage must be 1. Okay, so we start with the solution to this LP. I'm going to slightly reformulate this by saying, you know, if I look at a set S, I'm basically going to imagine replacing it by a path that goes through all of the nodes in that set S and reaches the root. Okay. Again, we don't care about constant factors, so one can choose such a path which has approximately the correct cost. Okay, so now we have a fractional collection of paths, again with a nice coverage property. So that's our starting point. And now we're going to gradually turn this into an integral solution. And the way we're going to do it is we're going to keep track of a solution that's part fractional, part integral. So the integral part is just going to be and each day is going to be a tree containing the root. Okay, so this we'll call the core. Okay, so that's some subtree connecting to the root. Everyone in that subtree is visited on that day and is fully paid for in the integral part of the solution. And then we still have the fractional part, which are these paths. But these paths don't have to go all the way to the root anymore. They just need to go and reach the core. Okay, once they reach the core, they can stop. We just need to pay for that part. And so again, we start with a fully fractional solution. So that means the core is empty. That's just this solution I described here. And at the end, we're going to have a fully integral solution where everything is in the core and there's no fractional part. Then we have an integral solution. So our goal is to find a way to adjust our current solution and add edges to the core and sort of remove weight, remove cost from the fractional part in such a way that our expected increase in the core cost is bounded by our desired approximation factor, log number of levels, times the expected decrease in the fractional cost. Okay, if we can achieve this, we're done.
4 minutes, Neil.
Thank you. How are we going to achieve this? So the first thing we're going to do is a simple sampling procedure, randomized sampling procedure, and it's the simplest thing you could do, independent sampling. So for each day and each path P that has some weight, we look at that weight. Okay, we'll upsample this by our approximation factor. And then we sample it with that probability. Okay, so if the weight was already bigger than like 1 over log number of levels, we would sample with probability 1. Okay, so this expected, so the expected increase in the core cost here is bounded by log number of levels times the sum of the weights of the paths times the cost of these paths. Okay, so that's what we do. So that increases the size of our core. So maybe I sample these two paths completely independently. And now I need to find a way of decreasing my fractional solution cost. Okay, so now I'm going to look at a single path and a single day T. Okay, so this is some particular path P. Now, of course, if I happen to sample this path, well, then I can just remove it all from my fractional solution. But let's imagine that the weight of this path is very tiny. The probability of sampling it is very small. So that's unlikely to happen. Instead, what we're going to try and aim to do is delete each edge of the path with some constant probability. Then we get what we want, because then our expected decrease in fractional cost will be within log number of levels times the expected increase in the integral cost. Okay. Now, how could this happen? Easiest thing that could happen is that remember, there are all these other paths that are around. And maybe one of these, maybe a path through this point gets sampled. Then I can delete this edge without any problem, right? Because this guy is already now connected by some new path to the root. However, that's again going to be very unlikely. And instead, what we will try to do is so imagine looking at this guy here, okay? Maybe no path at day T through this node is sampled, but maybe at some other day, T prime, such a path is sampled. And this if this Dayt prime is in the time window of everything in this subpath here, we can move that subpath to this other Dayt prime in order to reconnect all of these guys. Okay, so that's the plan. So we want to sample, then we want to find a way of splitting my path into pieces and then shifting each of these subpaths into a new day such that we're again feasible. If we can do this, then we succeed. So I won't I don't think I have time to explain exactly how this works, except to say that yeah, just the very brief idea is that somehow things are great if you have the like this edge here is very good in the sense that if anyone in this interval connects, right? So if anyone in this interval has samples a path to the root at some point, because these intervals below it are bigger, I can just shift this whole path to this new location here. Things are trickier when the situation at the top where, you know, this point here is outside of the intervals below it. And so, yeah, there's some union bound argument, which is where the log number of levels comes in. So let me maybe not attempt to describe that in more detail. Let me skip to the conclusion. So yeah, so we get this exponential improvement. And I'm not going to talk about it, of course, but we also get the same approximation bound for submodular JRP. The rounding is actually completely different. It has essentially nothing in common with the rounding for IRP, though the simplification to these left-aligned instances is exactly the same. Okay. And again, the open problem is constant approximation for both problems. So let me stop here and ask if there are any.
Okay, thank you very much. So are there any questions from the audience? I don't see any hand raised. Let me just meanwhile ask a very probably, you know, a natural question like, is it important that you have only one depot?
Yes, I mean, definitely. We didn't think about the sort of the multi-depot setting at all, to be honest. Yeah, I think it matters. I'm not sure if the arguments can be made to extend these. I mean, I guess even the single day problem gets harder. It's no longer TSP, but I guess it's one of these vehicle routing problems that is known. Yeah, it's a good question. Don't know.
Okay, good. Any other question? Okay, seems not. Yeah, no, we have one. Okay, Joe, you can unmute yourself. Yeah.
Nice talk, Neil.
Thanks.
So you mentioned that these approximation factors, the constants, you don't care about, or you're brushing under the rug.
Yes. Yeah. How big are the constants? I think they're not crazy. I'm trying to remember. I don't remember.
Okay.
Yeah, let me answer that on Slack.
Yeah.
You should look at the paper. I think they're not crazy, but on the other hand, it's also they're not like 2 or 4. They're probably somewhere between 10 and 100, I guess.
Okay, thanks.
Let's see another question.
We have another question from Roland Wins. You can go ahead unmuting.
I can read the questions actually. So,
okay, then I just lost it. So is this interval laminar setting, this can be generalized by losing only a constant factor?
Yes. So so what we show is that so for a general collection of intervals, we can reduce it to this left aligned setting. So it's not quite laminar, but it's sort of like laminar from the perspective of the left-hand sides of the interval. And that is a bit harder to deal with than laminar intervals, but sort of one just needs one extra ingredient over the laminar case to handle it. So I didn't even really talk about how the shifting procedure works for the laminar case, but then there's basically a situation where you look at what works for the laminar case, and kind of like if you're able to only shift these paths to earlier days, then everything is fine. But shifting to the right, because you only have the structure on the left endpoint, shifting things to the right doesn't work. So you use an extra trick that basically allows you to only shift to the left, and then things work.
Okay. Any other question? Okay, so if not, yeah, we can all unmute and give a round of applause to Neil for this very nice talk.